When you're ready.
Okay. Good afternoon. I'm Jeff Havens. I'm the technical lead for Win64, and specifically IA-64, which is now I'm only supposed to call it titanium. But old habits die hard. I just got used to not calling it percent. This is sort of a how does IA-64 architecture work kind of talk, plus a little bit about debugging. I've given this talk internally to several groups. I've never lost the entire group yet. I usually fall asleep first. So if you have any questions about IA-64 or Win64 in general, I should be able to answer them. I have in my past life worked on I/O and file systems also, but I have forgotten all of that. IA-64 has a huge context, large number of registers, and the number of registers you have available to you is variable, and we'll talk about that a little bit. As you can see at the top of the slide, it takes 3 slides just to show you how many registers there are. There's a set of general registers, of which the first 31 are available all the time. Register 0 is a known value of 0. We have an instruction register, branch registers, which we use to define the target of a branch, and some predicate registers, which we'll talk about some more also. We have large floating point context. Floating point registers, the first 31 are available in the kernel as well as in user mode, but we don't let you. There are actually 128 registers, but the 32 through 197 we don't use in the kernel. There's a switch on the compiler that's set by default that says don't use those upper registers. The reason floating points is available is because multiply and divide use floating point. So if you're going through some disassembly and you start seeing these things like XMA and things that look like floating point, probably what's happening is you're doing a multiply and divide. At that point, my eyes glaze over and I look towards the end and figure out when it's moving it back to an integer register. The application registers we don't use very much. There are some other registers that control the state. Basically, they're like stack pointer registers. And a few other things that you can read about as far as loop counting registers and stuff like that. The LC register is loop counting. This is used in call stacks, and we'll get to that. The current frame marker defines how big the stacked registers are. We have a nice little example, which I stole from Intel, about how that all works. Basically, the only things that are interesting are the size of the local and the size of the frame. One of the features that IA-64 has in it is what is called rotating registers, and this lets you write really tight loops, but still have allow you to effectively unroll it. So you can do a load, and then like 3 times through the loop later, you actually use the results of that load. And this is so you can write more compact code, yet still hide some of the latency. One of the neat features that is in the IA-64 architecture is called predication. Basically, almost all the instructions in the instruction set can individually be disabled or turned off or on based on one of the predicate values. Now, by default, when you look at instructions, they're all predicated to true because because most of the time you want to execute your instructions. So, for example, if you have a simple if statement like we have shown here, you would normally have to take a couple jumps as far as executing this if statement. Rather than do that, you can just set the predicate registers, and then individually, if P2 is set to 1, then we'll execute these 2 instructions, but we won't execute these 2 instructions. So this way it's straight line code. You don't have to confuse the prefetcher or the branch predictor, or none of that stuff gets invoked. It just runs through and executes. The downside is that these instructions still actually take resources in the processor. So you won't see, 20 lines of assembly code all predicated off, because in that kind of case, it's faster to just take the branch and branch around a lot of code if you're not going to execute it. So like if this was an add, it still uses the adder resources in the processor. It's just that we don't ever save the result in a register. Or in the case of a branch, we don't take the branch, which is actually something we'll show you later. So consequently, you don't actually see a lot of code predicated on or off except for conditional branches. I like this table a little better about sort of defining what some of the registers are. Register 0 is always 0. Register 1 is a special register, and the disassembler calls it GP. We'll talk about what that means. R2 and R3 are scratch registers. 4 through 7 are preserved registers or saved registers, so they're saved across system calls. Turns out we don't actually use these very often, and you'll see why when we talk about the register stack. Return values from functions are returned in register 8, 9, 10, 11, basically register 8. If you're returning like a 128-bit structure or 256-byte structure, then we'll use those other registers. Register 12 is actually the stack pointer. There's nothing special in the processor dealing with the stack pointer, but of course the OS uses it heavily. The thread pointer, or the TEB, is actually stored in R13, both, and that's true for user and kernel mode stack. And then we have a bunch more stack scratch registers, which register 14 through 13. Then you can have a variable amount of the stacked registers starting at register 13. Parameters get stored, basically scalars and stuff that we usually deal with in the kernel, pointers, lengths and stuff like that, all get stored in what are called the out registers. The out registers are really start at register 32 and go on. Now, if your function has more than 8 parameters, then we start spilling those parameters off into the stack, which makes them harder to find. So here's an example of the register stack, and you can't quite read that yellow there. Basically, when you're in a function, your registers, the registers from 32 and above are divided into 2 groups. There's the locals and the outputs. The outputs are exactly what you think they are. They're where you're going to put your out parameters when you make your next function call. And then your locals include any parameters that were passed into you, as well as any local registers you might be using. Basically, what happens is the compiler keeps your functional state that you carry along as you make your function calls in the first set of registers. So in this case, from 32 to 45, those are sort of your locals, as well as your arguments. So as you can see on the left, the current frame marker over here says we have, these are in decimal by the way, we have 14 locals and we we have a frame size of 21, so that means there's 7 output registers. If we turn around and function A calls the ever-present function B and make a call, what happens is what used to be register 46 in function A now becomes register 32. So 46 was the first output register, so now it becomes register 32, so that's our first argument register. So our first parameter is stored in register 32. You can always find it that way. The other thing is that now function B actually only has seven registers. Where this one had 21 registers. This guy only has 7 registers. So his register frame size goes from register 0 up to register 39. The other thing that happens is, as part of the call chaining, we move current frame marker and previous frame marker. One of the things about the frame marker, the current frame marker, is you can't really change it directly. Then, typically the first thing a function will do is it'll execute an alloc instruction because it wants more registers than what it has. So what the alloc instruction does is it extends the register frame that this function has. So we executed an alloc instruction. We had our inputs here ready. We said, gee, I want some locals of, looks like about 9 more local registers. And then we're going to call the functions with 3 or 4 more output registers. So now, where before my highest register was 38, now my highest register is 50. This allows you to the function call passing and chaining to be very fast. All these registers are actually contained in the processor. They're sort of cached up as part of the state of the processor. So you can, in theory, make a function call, allocate a bunch of registers, do some stuff, return back, and never have to do any memory accesses to access all these registers. It's kind of like the opposite of x86, where everything has to go in and out of the stack, and there weren't many registers. Now we have lots of registers, and you tend not to use as much on the stack. Continuing on with our example, you can actually see what happens here is the current frame marker became this. It said we have 15 locals and 19, and a total of 19 registers. The chip actually does not care what you specify as the number of inputs are once you get in here. There's nothing interesting about what this line is as far as the process is concerned. In fact, this whole line, this whole thing can actually be smaller than what you originally had. It's just sort of a pointer that gets moved around. There's these 2 pointers, because this one is important when you do a call instruction. Then when we do a return, the thing just gets unwound. So a return puts this back into here and moves the backing score pointer back to here, so the A gets back what it had before. Now these registers, if function B changes these registers, like they modify their arguments or something like that, then A will see those modifications. So they're basically garbage at this point. They're like temporaries. But all these values, B cannot actually physically touch or change these. So, when you make a function call, all this state is completely preserved. And as we'll see a little bit later, it actually makes debugging a lot easier, because you can find out, well, what is my ERP pointer? Well, you don't have to go dig it off the stack and figure out where it was stored. Your ERP pointer is probably right there as our register 32, and nobody can touch it except this function in the debugger. Hopefully he's not doing too much behind your back. Because the register stack is so important, we invented a new command. It actually isn't a new command. x86 had this, but we didn't use it very much. Called KV. What this does is it displays the local part of that picture for you for each function as you go back on the stack. Since the output registers are actually part of the next function called frame, we don't display the output registers. So sometimes you might see, well, I'll show you an example. As I say, R32 is normally the first argument. Unless you're writing C++ code, if it's a method, then R32 is this pointer, and the first argument is pushed down to R33. Only the first 8 values are stored on the register or in the registers. After that, we spill to the stack, and then it's up to you to figure out where it's actually SP plus 10. There's some impetus. There's some virtue to not writing arguments or functions with lots of arguments. So this is why I actually wanted the slides printed out for our iTest today. If it wasn't printed out, they're not very easy. So there's lots of nice information here. We have our stack pointer. As you can see, the stack pointers are our full 64-bit values. I actually debugged a case where we had a bug where the stack actually straddled a 64 gigabyte boundary. So the top of the stack was like 164 mumble, and the bottom of the stack was 165. So somebody was comparing the stack bounds, and they were doing a 32-bit compare and a 64-bit compare, and they failed their compare because they expected the top, or the 32-bit wise looked like the stack values were reversed. The top and bottom were reversed. So when you're probably wondering, well, when things get into register stack and go deeper and deeper, where does all these data values go? When I'm way deep, when I'm 100 levels deep, like in IFS grade file, what happens is they get stored on something called the backing store stack. IA-64 actually has two stack pointer. There's the normal regular stack pointer, and it grows downward. I grow my text down. And then the backing store stack goes upward with increasing addresses as you go up, until there are actually 2 limits that you can overflow when you do too much in your NTFS grade file. We've overflowed both of them in our development process. And it's in the backing store stack that we actually save all the stacked registers. So what really is happening with KV is all it's really doing is pumping what's called the BSP stack. So if you were to say DD or DQ, quad words, on this value, you would see these values printed out. But we just make it so you don't have to sit there and go, oh, well, the first ones are, which one's R45? You don't know how many times I counted. Okay, R32, 33. So now I can go find like R43 pretty quickly with this kind of display. And in this you can find all your state. Like for example, here we have a case where we're calling our friend EXAllocate pool and tag. Well, the first argument is EXAllocate 9, which I think means allocate page pool, and raise an exception if that's true. Second argument is I'm asking for 438 bytes, and the third argument is the tag. So you can just read all that stuff right off there. And as you're looking at a disassembly of the EXAllocate pool, you can find all the registers and pointers to things that you would have found, or that you might want to find when you're trying to debug this. It's rather ironic, but when I was updating these slides, I could not actually find, I didn't actually have any interesting crashes to look at, so I actually made one up. We'll see that more as we go along. I mentioned the GP, which is global pointer addressing. This is something that's been done in a number of in a lot of the RISC architectures. When you're trying to do things like have all your code be position independent as well as fast, having to generate a 64-bit pointer for every address you're looking for gets to be a lot of work and makes your code undense or not very dense. So what we do is we have a section in the image where we put all the short data items and pointers to other things. And when for each module we do this. When we come into each module, when we enter the module, this pointer is set up in register 1. It's part of the calling convention that this value be set. When you make a call out to another module, you're not guaranteed that it's not saved, so when you return, you have to restore it. So for example, each driver has its own GP address, and the kernel has its own GP address. Small data items like 8-byte pointers and things like that can be stored in the GP area. So in order to support the GP addressing as is done with, this was actually done in PowerPC 2, if you go back that far. Function pointers or the symbol like KE wait for a single object, that symbol in the C code does not actually point to the code you want to execute. It actually points to a thing called a function pointer, and in a function pointer there are two pointers. One is a pointer to the code, the other one is a pointer to the GP value for that module that you want to execute. The compiler pretty much hides all this from you. Your C code, it all just sort of works out. Occasionally you stumble across it in the debugger. The other people who get tripped up by this are people writing assembly stubs. Basically, you have to solve all your problems by an additional level of indirection. In the code, or as far as the linker and everything goes, what happens is a function will actually have two names. One is the traditional name, and then the other one will have a dot prepended in front of it. The one with the dot prepended in front of it is actually the symbol for the code, and it's what you branch to. The debugger pretty much hides the issues with the dots for you, so you don't have to worry about that too much. Branches are either PC relative or indirect off of one of the 7 or 8 branch registers. When we make a call, the return value would be 0, and all the conditional branches are controlled by predicates. So we have an example here of a conditional branch. We're inside access fault, just stepping through the code. This is a compare instruction right here, and we're comparing register 31 to 1, and that sets predicate register 15 and 14. If the compare is true, then predicate 15 will get set and 14 will get cleared. If it's not true, the opposite will happen. IA-64 has like 9 or 10 different compare styles. Styles about how these predicate registers are done. You can probably do a small master's thesis on these instructions. But basically, these guys are the simple ones that you can do. So if we step through the code a little bit, look at register 31, we see it's 0. So our CS background would predict that register 15 should be 0. Predicate 15 would be 0, that's correct. And predicate 14 would be true. And for those of you who are hardcore, you can go figure out which bits these are here. When we first started bringing up IA-64, we only had this, and I actually learned which bit these were. Fortunately, the compiler only used 14 and 15 at the time, so I only had to look at 2 of those bits, so it's okay. If you keep stepping through, now we've advanced out of the dark ages, and we go to a conditional compare. The debugger will actually tell you, oh, by the way, predicate 14 is true, so this means we're going to take this branch and branch to this address. Sure enough, when we step over it, we go in the right place.
Just out of curiosity, what is this notation where you've got a command and a dot and then an extension on the end of it, especially in the case of like no-ops? Isn't a no-op?
IA-64 is actually not a RISC instruction set, so we have different kinds of no-ops. There are at least 4 or 5 of those. Not to mention, we have all these fine things. To answer your specific question, this is a no-op which uses the math resource. And there's like a no-op F, which uses a floating point resource. There's a no-op I believe, which uses the integer resources. The true answer is you can ignore it. You can ignore, in most cases, you can ignore this stuff after the dots. You can also ignore these little semicolons, but I'll tell you what they're for. Probably, I'll save that one for the next slide. What this means is these are hints to the processor to tell it what's going to happen. So this is a branch, it's conditional, it's dynamically predicated, and it's probably taken most of the time. The compiler believes anyway. And the prefetcher should only grab a few instructions based on this predicated taken because the compiler's only got a 50-50 chance. This particular predicate, by the way, is this a user mode or kernel mode access mode? So the compiler probably doesn't know which one it is. So that's all the stuff in here. There's actually some more things you can do, believe it or not. But I'll talk about semicolons in a second when we get to full disassembly. Which I think is good. Okay. So we talked about the function pointers, and this gives you a little bit all the code in one thing. A couple of comments. First of all, if you are using Ntsd as your debugger, which is what I use, I can't help it. If you are using that, you want at least 100 columns wide because these pointers get really big, and not to mention you have all this garbage in the disassembly. The other thing is, I will say that WinDebug is a lot better. It's based on the same back end, so you can see the same kind of things. I just haven't switched over to start using it, and it makes this a little harder to do. A couple other things about debugging and WinDebug and Ntsd. You may not believe it in this talk, but it's actually easier to debug optimized IA-64 code if you're debugging at the assembly level than it is at the unoptimized code. The reason is IA-64 load instructions. There's no index displacement for one thing. So like when the debugger or when the code is storing everything on the stack, storing all your variables on the stack, it means it has to generate an address for every one of those stacks and put it in the register. So for like unoptimized codes, you'll see the compiler generate use six different registers to give one address to I for your loop count, and trying to figure out, well, which one, when it loads something out of memory, if you got 20 variables on the stack, it's really hard to figure out. Anyway, that's sort of an aside. So the question was, well, what are these curly brackets and what are these semicolons? IA-64 bundles its instructions into three instructions per bundle, and all the instructions can be executed in parallel at the same time. However, you know, life is not that simple, and so maybe you can't get 3 instructions you want to execute at the same time. So these are called stop bits, and they say, okay, all the instructions, these 3 instructions can be executed in parallel, but for example, between semicolons, the instructions cannot be executed in parallel. And a good example that this instruction here is a load, and it's also an auto increment of 8, so it modifies this register. So we can't do this load and this load at the same time because this register is being changed. So there's a dependency between these 2 loads. So what the code's doing here is we start out and we calculate an address off a GP value. So the debugger says, hey, hex values can't possibly be negative, so we display it as a 64-bit number with lots of F's in it. So that gets us a pointer to the function address pointer, and we load that, and we get our into R28, and now R28 now points to the function pointer which I described earlier. We load that value into R27, so that's actually the pointer to where we're going to jump to. We increment it by 8, and we load the GP value, which we're going to pass to our caller. And then we move this value into a branch register, and then we do a call with our dynamic taken many on it. And what this says is we're going to branch B6, and we're going to put the return value in RP, which is actually B0. So if we go look at this and say, gosh, if we dump this value out, LN tells us the address. We see that this is the import for KD check. And if we, so this is, that's the import. This is actually the function pointer. If we dump the function pointer, you see here we have an address. And then this would be the GP value. And if you do an LN on there, you'll see that there's the dot there that says this is KD check. Any questions on that? Light, not very good slide. As invariably happens, the kernel guys change something in the system, and they cause your driver to take a trap. And so you got to figure out, well, what happened? Why did my driver take a trap? And this, like I say, I didn't have a good trap, so I just set a breakpoint on MMAxis fault. So this is actually just a standard old page fault is what happened here. So you get a stack trace like this. Usually what happens up on the top is a KE bug check, 5A or some other exciting thing. And now, so what you do is you go find that key thing like K general exception handler. It may have some slightly different name than general in there. There's a couple others, but it's usually pretty obvious where we took the exception. And you go find the stack pointer for it. And then you say dot trap against using that stack pointer value. And basically at that point, it'll dump out your whole context of your function at the time the trap occurred. Again, this is one of these 3-page slides. We start out with our floating point values. For the CS savvy among you, I think these are actually all integers being stored in there because that's what we were probably doing with multiplying and stuff. We print out the backing store value at the time of the trap. This is not really interesting except to anybody, even me, and I put it in there. This is our GP value at the time we took the trap. And then On the following page, we have even more state. As you can see, this is a function that uses a lot of registers. It has up to 58 registers that it's using. Now, what to say about that? Down near the bottom is some of the interesting bits. This is actually the trap information. So we have the PSR at the time of the stack, the faulting address, which is actually the value we faulted on, the instruction pointer that faulted modulo 16. As I said, instructions. The instruction pointer on IA-64 is actually an instruction bundle pointer. So a bundle is 128 bits, so it's always aligned on 128 byte boundary. But there are 3 instructions in each bundle: bang, trap, and the debugger. What we actually do is we say, okay, the first instruction in the bundle is 0, second instruction is 4, and the third instruction is 8. Instructions are actually 41 bits, so they don't line up on nice boundaries like that. They don't line up on any boundaries. But that's the convention we use through the debugger. So when the debugger reports this error, it says, oh, this was at 8.4. And so we know that tells us it's actually the second instruction in the bundle. One of the really handy features, which I've been using a lot lately, is IIPA. This is the address of the previous bundle was successfully executed. So if the debugger happens to come in and really screw up your context, and you do a return back to 0, or you jump to 0, or something like that, you can go look at the IIPA and see what instruction caused that jump, and at least have some clue as to where you came from. What else interesting is in here? The other thing bang trap attempts to do, and we're fixing this still, is you'll actually set your context to the function at the point where the exception happened. So you can say, oh, R26, do an R26 after you've done a bang trap. The debugger warns you and says, hey, you're using this based on your last context. The address of the contents of that register is this value, which I picked because, gosh, it's a score into R26. And if we go look and say, oh yeah, that was the faulting address, sure enough, everything looks consistent. So you can figure out, well, why did I take this fault? And by the way, that address was on a page boundary. That was because we were ending up allocating the page. Some other features. My experience with IA-64 code, even optimized code, is that the line numbers are pretty close to right, especially with instructions that cause faults and things like that. So when you're building your own binary and your own driver, you can build with the full symbols and get the line number information and get a pretty good look at where you're at. If you enable the line number stuff, it shows up in stack traces and LNs and things in various places. So the first one, .line, says load the line number information. Second one says something else, which is turn it on for LN and prompts. So then, but you don't get this. You don't get the kernel information in the DDK and stuff like that for the line numbers. You get a bunch give us there. So this says, oh gee, I'm at line 344 of MMX's fault in our code. Another nifty feature that IA-64 has is run to next taken branch. When you have functions that have, say, that are 8K of assembly code or of object code, why it's sometimes hard to just kind of walk through those, especially with all the no-ops and adds and everything. It's pretty boring. So we have run to take a branch, so you can sort of trace through a function until you get to the point where you're interested in. What this instruction does is it prints out where did I come from based on IIPA and where did I go to. So I ran for a while up to C00, and then I ran for a while and went from executed about 3 bundles, then I took a branch to D50. So I came from C020 and I went to D50. So that makes it easy to walk through. You really want this value because all of a sudden you'll be in some function and mentally you say, how did I get here? Then in that case you can just say like go after RA to branch back and increase the function. This has been pretty quick with a lot of information, but it gives you an idea of what some of this stuff is. Intel has put a lot of stuff about IA-64 on their website, all levels of detail, including how to optimize for the processor. My advice is don't write assembly code. The compiler guys know more than myself anyway. They also have some little tutorials about how this stuff works. They talk about features, why IA-64 is a great thing. And then, since this was sort of a debugging talk, we also have our debugger, which I'm sure you're familiar with. One other thing, since I pulled this up, I wanted to show some real-time case here. Another feature of IA-64 is is what we call speculative loads, and this is the compiler says, well, chances are I'm going to want to load this value, but we haven't had time to test it for all yet to see if it's really I don't really want this value. And what you can do, what the compiler can do or the chip can do is say, I want to try and load this. If it doesn't work, we'll check later to see if it worked, but I want to start the load now so that it can come up through the, from main memory, from L3, L2, L0, L1 caches, and I want to get that process going a little bit ahead to reduce latency and improve performance. So, because most of the time, we're doing a load, the pointer's not null, and we're going to go ahead and take it. So what we do here is, at this point, this is just some code I mentally pulled out. We have what's called a load8.s, which is load8 speculative. And what that means is if for some reason R31 faults, for any reason R31 faults, nothing much happens except that there's a magic bit in R30. The registers are actually 65 bits. And the 65th bit is used to indicate whether the value is valid or not. And we call these invalid values nats, for not a thing, which is comparable to not a number in floating point. So what we do is we do a speculative load at this point.
Does the value get overwritten?
Does the value get, the architecture says the value is undefined. So, you do a speculative load with the anticipation that the load actually will occur. If it doesn't occur, it's garbage. And essentially the register is actually poisoned. If you did one of these speculative loads and it failed and you attempted to use R30 or something, like store it, if you attempted to store it or put it in a branch register or something like that, the processor will fault and will raise an exception. Typically, code executing doesn't ever have this happen to it. So in some respects, you can kind of ignore this load S because the interesting thing, it doesn't happen here. So what happens is we attempt to load it, assuming the compiler works right. We have seen some of these where the compiler didn't quite check the register. So what happens is we come in and look at R30, and we say, or we load off R31 into R30. Right here, we're doing a comparison R35 to null. And if that happened, then we're going to branch out of this area. But otherwise, we come down in here and we say, then we do a check on the value of R30. And this check says if the previous load speculative didn't work, then I want you to go to this address and execute that code. If it did work, we just drop through and start executing. And as you can see, we start using R30, or we start using R30 to do other things. This is a so-so example because you could, even if R30 was a NAT, you could actually execute this instruction. All that happened is the OR would cause the NAT to get propagated into R39 as opposed to R30. But in case of the check, we come down, we do the check. What would happen is we would branch to this piece of code here where we would actually do a real load. So let's say R31 was null. Well, this branch test didn't test R31, so R31 could be null at this point. We would come down here, R30 would be NAT, would have the NAT, we would branch down to this point. Then at this point, we would do a load of R31. If R31 really wasn't valid at this point, we would fault. So what I mean by, gee, you can usually ignore these load speculative checks is when your AV comes, it'll come at this point, and you'll just say, oh, look, I'm doing a load 30 off of R31. But if it was the case that whatever R31 pointed to was just a pace of paged out data, at this point, we would take a page call, context switch away, load it back up, paste the page back in, and start the thread. We would start executing. At this point, the load would complete. We would continue on our execution and then branch back to the mainline path, which you can see is actually where this guy ended up going. So that's how the speculative stuff works. And if you are working through this code, you'll see these speculative things. These speculative loads, the compiler likes them. So it can load the things in advance of where you're at. So that gives you an idea of what you're dealing with the IA-64 stuff. Questions?
A little bit orthogonal, but with Windows 2000 we were restricted to a 12K stack. I'm wondering with IA-64 where a stack is.
I forget how big it is. First off, with IA-64 we have 8K pages, so that's bigger. I forget where we are. We're something like I think the stack for the stack pointer is something like 48K, and the backing store stack is 32K. So they're a lot bigger, but in the end, you can't really recurse anymore. It's just that IA-64 chews up a lot. First of all, the stack is, by definition, almost twice as big as far as saving and storing registers, since they're 64 bits. And things like trap frames are a lot bigger. So a trap frame is close to like 6K. Is a trap frame because you have all this floating point state and stuff like that. So the reason the stacks are bigger is because we were chewing them up.
Hey Jeff, how are return addresses stored throughout when you're calling stuff?
When you make the initial call, what happens? This is an easy segue here. Typically, a typical prologue for a function, what will happen is we'll save away, we'll do the alloc, and this instruction also saves the previous frame. Size, this helps us tells us how to unwind. So we'll store that in register 51. This is saving the predicates. This is adjusting the stack pointer. This saves the return value, which is in B0. It's typically just saved in register 50. Or it's typically saved in the stack register toward the end of your kernels.
It's still right next to all the parameters.
Well, it's actually, if you look at like a KV dump, it tends to be near the bottom, not near the top. The
Okay.
parameters are near
I
the
was
top.
thinking trying to feed people the right viruses that take advantage of buffer overflows.
Ah,
If it was
well,
always
the nice thing is you can't easily do that. It's not so easy to do that because your buffer is on the stack. This is on your register stack.
Okay.
So it's much harder to overwrite that.
Great.
It's in theory possible, but in fact, may not even store it in memory. When you make like a call, while you're executing, there's no place in memory where the RP is for the executing function. It's only in the state of the processor. Even if you make a call, the return pointer might not be there. So it's actually rather difficult to modify that pointer. Now, what happens when we go into the debugger is we go into a function and we flush all that stuff out into memory, and at that point it's modified. So the return pointer gets stored in the registers, and here we are, we're saving away GP because we're going to make a call. You'll always see this instruction. This is so we're touching the stack, and this is what causes your stack overflow, basically, unless it was an exception. But you know, as we work down and allocate to the stack, we always touch the bottom of the stack to make sure that it always is instantiated if necessary. So this is a very typical prologue. But these numbers are different in each call because these numbers typically are different.
How are the software breakpoints done?
Software breakpoints are done just like we do in x86. We go read the instruction, we put in the breakpoint in the register.
Do you replace one instruction in the bundle, or
Yes, we replace one instruction in the bundle. We talked about, you know, and you read the discussion about IA-64. You know, they make a big deal of explicitly parallel and executing these things in parallel and everything else. From the programmer's standpoint, from your from your standpoint, none of that matters. You can't tell whether they're executed or in parallel or not, because each instruction, if all three of these for some reason were to fault, you would only see the first fault. So faults are delivered in order. So the fact that these three instructions happen at the same time is irrelevant, because when you see the trap, it'll be the first one in program order that trapped. So when we set a breakpoint, we only would set a breakpoint here or here or here. When we say step or single step in assembly mode, it's one instruction at a time. So from that standpoint, all the parallelism and stuff does not affect you when you're looking at how things operate. Everything happens in order, in program execution order. Now, of course, what gets really exciting is things like the IA-64 architecture does allow for things like out-of-order writes. So if you have in a multi-processor case, it is possible for a processor over here to write location A and location B, and for processor 2 to observe location B written before location A. So you know, if you don't have spin locks around a spin lock will provide a barrier to prevent you from seeing that. But if you're to say, oh, well, I'm going to write this first, and then this piece of code over here is going to look and see what I wrote, that doesn't work.
Is in multiprocessor machines, is there cache coherency like on the x86 across the processors? Does it handle that automatically?
The processors are cache coherent and they're cache coherent with I/O. However, the order in which you see the effects is not the same. So on x86, we guarantee, if you run location A and then location B, there's no way this processor number 2 can see the write of B before A. So there's a whole section on ordered writes and loads and things like that. When you try and pin the CPU architects about, well, what does that really mean? They squirm a lot. The bottom line is, it's a good idea to put spin locks or resources around your data structures. If you have a variable that you're sharing, if you make it volatile, then we'll take a very conservative approach to that. We'll use special loads and special stores. Yes, there are more kinds of stores that chicks stick in also. Like or and so these loads and stores will help preserve the ordering a little better. But in general, things can get a little squirrely. We haven't seen a lot of those problems. Titanium isn't real aggressive about reordering writes, but with McKinley and the next version, we'll see some more of those issues. By the way, this is a load NTA, which is non-temporal access. What that means is, don't allocate any cache space for this because I'm not going to use it anymore. We're just loading it to touch the stack. Any other questions? But like I say, most of the time you can't do it. Okay.
Yeah. With Ntsd doesn't fill L2. It does with R3, right?